This video should help you get through the Introduction to Manufacturing Processes presentation. Before a product is manufactured, raw materials must be obtained. Raw materials are natural resources found on or in the earth or seas. They may be renewable or exhaustible. Renewable resources are usually biological. These include things like trees, cotton, wool, and animal products such as hides. Exhaustible resources cannot be replaced. Examples include metal ore, petroleum, natural gas, and coal. Primary processing is the first step in manufacturing. It is the point at which raw materials are changed into usable material. The three major procedures are thermal, which is heat, chemical, and mechanical. The resulting materials are referred to as industrial materials or standard stock. Secondary processes take the usable material and use it to create products. Common processes include casting and molding, forming, separating and joining, conditioning, assembling, and finishing. Consider this slide where we see mines extracting raw materials, and then that going into primary processing to give us bar stock, and then that being used as a secondary processing to create something like, say, a ladder. Now that you've seen an example, let's talk about how that process works. This is what I refer to as IPOF, you might remember from IED, Input, Process, Output, Feedback. Inputs, you put things into a system in order to receive outputs and achieve goals. These can be things like people, natural resources, capital, finance, knowledge, energy. Processes, where the actual work is done, can be transformation processes, management processes. If we take into consideration those two, transformation processes might mean something more like dealing directly with the inputs, use resources to create desired outputs. Whereas with management processes, we might be more thinking along the lines of they're used to ensure the effective use of resources. All actions ensure that the transformation acts are efficient and appropriate. Let's consider outputs next. Desired outputs, these may be manufactured products or constructed structures. Other outputs might include things like scrap, pollution, noise, fumes, etc. An output objective might be to produce the maximum amount of desired output with the minimum amount of undesired output. Let's consider feedback, a system that can use its own information to control itself. If measured output is not what is expected, corrective actions are implemented. An example of this, a thermostat. When the temperature is high enough in a room, the thermostat controls the heating and cooling systems in order to maintain the desired results. Let's consider ceramics as a material. Any of the various hard, brittle, heat-resistant, or corrosion-resistant materials made by shaping and then firing a non-metallic mineral like clay at a high temperature could be considered ceramics. Materials that are considered metals could be any of a category of electropositive elements that usually have a shiny surface, are generally good conductors of heat and electricity, and can be melted or fused, hammered into thin sheets, or drawn into wires. Plastics are materials that undergo a permanent change in shape or size when subjected to a particular amount of stress. Material properties for all of these things could include mechanical, which might mean something along the lines of compression or tension, physical, which might mean something more like size or density, thermal, such as melting and freezing points, chemical, like the ability to resist chemical change, such as corrosion. There could be material properties such as electrical and magnetic, things like conductivity, resistivity, and permeability. There's even optical, which could be things such as opacity and color. Or what about acoustical material properties, things that can be considered absorbent or allow for transmission or reflect of the sound that's around it? There are some other categories of materials to consider. Let's think about organic. This can be traced back to living organisms or parts of living organisms, things like coal or petroleum, wood, and wool. Or inorganic, non-living ores and earth elements such as copper, gold, aluminum, glass, and even cement. There's even engineering materials to consider, solid structure, which will hold their shape without outside support. And then right along with engineering materials would be non-engineering materials. Gases and liquids. These must have a container if they are to be contained or held in a particular shape. Then you have metallic materials, most widely used group of engineering materials. These are pure metals and alloys. You can break those down into ferrous metals. Iron is the principal ingredient there, and non-ferrous metals. Iron is not the principal ingredient for those. There's also polymeric materials, organic or non-crystalline things. Natural things might be considered wood or wool, latex, cotton, or silk. Synthetic ones, plastics mostly, we have thermoplastic or thermosetting, elastomer. Thermoplastics can be heated and reformed repeatedly. Thermosets, once molded, these materials resist heat. Handles of a toaster is a good example, maybe an iron or kettle. Then there's ceramics, clays, cements, plaster, glass, abrasive, and porcelain. Composites, combinations of two or more materials, is one of our last ones to consider. Each material in these retains its original properties in order to overcome the weakness of another. Let's watch a video on composite materials.
Composites are made up of at least two distinct intended materials which together improve product performance and/or lower manufacturing costs. Many materials routinely designated by other terms are also considered composites, including plated, clad, or coated metals. The term composite, however, has come to mean a material consisting of a matrix or base material and a reinforcement material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the part. The primary purpose of the matrix is to transfer the load or stress applied to the composite to the reinforcement. The matrix also protects the reinforcement from adverse environmental effects. The reinforcement's function is to improve the mechanical properties of the composite and is typically the main load-bearing element. Reinforcement is usually in the form of fibers or particles.
Let's consider some things when selecting materials. Things such as internal structure, property, or even the conditions of the materials themselves. Physical properties might include things such as density or porosity, moisture content, or surface texture. Mechanical properties might include things such as type of bonding that's needed, the number and types of imperfections in the material, its strength, the material's plasticity or ductility, its elasticity, or its hardness. Let's consider casting and molding. Molding is the process of manufacturing by shaping pliable raw material using a rigid frame or model called a mold. Plastics are a popular type of material used in this process. Casting is a manufacturing process by which a molten material, such as metal or plastic, is introduced into a mold, allowed to solidify within the mold, and then ejected or broken out to make a fabricated part. Here we have an artist's rendition of an injection molding machine on the left, and on the right is a robot assisting with sand casting. Let's watch a few videos on the different types of casting and molding.
Casting is the solidification of molten metal that is poured into a mold or injected into a die having a cavity in the shape of the desired part. Casting is used in virtually every industry, since all metals can be cast. Even mill forms, such as bar and plate, are produced from cast metal. Casting is usually the quickest way to shape metal into a part. Because of this, casting is used both for prototyping as well as production of large quantity parts. Casting processes can be grouped into three classifications: expendable mold, reusable pattern processes; expendable mold, expendable pattern processes; and permanent mold, no pattern processes. Which casting process to choose depends on part size, part configuration, part quantity, required tolerances, and the metal specified. Die casting is a rapid, high production process for simple or complex, often thin-wall, precision parts. Castings are usually small to moderate in size and cast of non-ferrous metals. The molten metal is forced under high pressure into the die of a horizontal, sometimes vertical, die casting machine. One die half is attached to a fixed platen, the other die half to a movable platen. Die casting can produce a single part or multiple parts in a single metal charge, also called a shot.
Injection molding is the most common method of producing parts out of plastic material. The process involves injecting molten plastic at high pressure into a mold shaped in the form of a part. Once this plastic cools and solidifies, the mold opens and the part is ejected. Injection molding is an extremely versatile process that can produce parts with holes, springs, threads, hinges, and undercuts in a single operation. Injection molded parts can be simple or complex, and can be solid, foamed, reinforced, or filled. They can be small or large, thick or thin, flexible or rigid. Injection molded parts also lend themselves to endless decorative effects. They can be polished, textured, hot stamped, plated, colored, or clear. No other manufacturing process offers the range of capabilities injection molding provides. Injection molding machines range in size and complexity from desk-size units up to machines the size of a small house. All injection molding machines are a combination of two systems: an injection system and a clamping system. The injection system heats the thermoplastic material to its appropriate viscosity or flowability and then forcefully injects it into the mold. There are two types of injection mechanisms: the reciprocating screw, which is the most common, and the two-stage screw. The main parts of the reciprocating screw injection system are the hopper, a reciprocating screw inside an externally heated injection barrel, a hydraulic motor, and an injection cylinder. Resin material is fed to the injection barrel from the hopper. These hoppers may be filled manually or vacuum-fed automatically, and often have dryers attached to the top to remove the moisture from the material. As the resin enters the injection barrel, it is driven forward by the rotation of the screw, which is powered by the hydraulic motor. The resin plasticizes or melts as the turning screw drags it towards the nozzle end. This is referred to as drag flow. Drag flow causes the polymer molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the injection barrel. The heating bands bring the material to its final temperature and compensate for the radiation heat loss. The temperature is controlled by 3 thermocouples in the barrel and 1 in the nozzle. The screw consists of 3 zones. The first zone, which is 1/2 of the screw, is called the feed zone. It has a constant flight depth, which forces the material together and rids it of air. The second zone, called the melt zone, has a decreasing flight depth, which reduces the plastic volume. This causes the plastic molecules to rub harder against each other, plasticizing the material. The melt zone leads to the third, or metering zone. The metering zone has a constant flight depth much smaller than that of the feed zone. This section acts as a pump. The tip of the screw has a one-way valve which lets the material flow only towards the nozzle end. The force of the plasticized material pushes the screw back as it turns. This builds a chamber of plastic in front of the screw. When enough material for the injection shot is melted, the screw stops and pulls back to decompress the material. For injecting the material, the one-way valve closes as the screw is hydraulically pushed forward by the injection cylinder. This sends the molten material through the injection unit's nozzle and into the injection mold. The primary speed and the injection pressure, called the packing pressure, is high, usually around 20,000 psi, but sometimes reaching up to 30,000 psi or higher. A secondary lower pressure is applied shortly after the initial injection. At the time of injection, the material's temperature ranges from approximately 320 to 600 degrees Fahrenheit, or 160 to 320 degrees Celsius. Once the plastic solidifies, no more pressure can be exerted upon it in the mold. The reciprocating screw then begins to rotate again, melting material for the next shot.
Let's move on to the separating process. This is one of the oldest processes. Chip forming subtractive processes are a type of separation process where a chip is formed. Good examples of this include cutting with a saw, drilling with a drill, or machining with a mill or lathe. Non-chip forming processes are a type of separation process where no chips are produced. Good examples of this would be stamping or shearing. Some processes use an electric arc to cut material. One such example is EDM, electrical discharge machining, which is used to cut holes in metal. Laser cutting is considered one type of separating processes. Let's watch a video on it.
Laser cutting uses a beam of laser light to generate heat for cutting metals and other materials. Laser's advantages over other thermal cutting processes include a narrower kerf, narrower heat-affected zone, and finer edge. Cuts achievable with a laser are smoother than with other thermal processes and may require no secondary edge finishing. Sheet metal may be contour cut rapidly, and small holes can be drilled in under a second. Laser cutting also has limitations. It is expensive and generally cost-effective only for materials up to 1/2 inch or 13 millimeters thick, though thicker materials may be cut. The term laser is an acronym for light amplification by the stimulated emission of radiation. A laser produces an intense beam of coherent light, as opposed to ordinary random light.
I'm fairly confident that you're familiar with laser cutting, but you may not be as familiar with Oxy-Fuel cutting. This video, however, is not very good on YouTube, so I'm going to show you how to find it on PLTW's courses site. If you navigate to Activity 2.2.2, Manufacturing Processes, and look under the Manufacturing Processes videos, you'll find copies of pretty much every type of video we're going to watch throughout this entire lesson. Down towards the bottom, you will find Oxy-Fuel cutting. Let's take a look at this one now.
Oxygen fuel, or Oxy-Fuel cutting, was once the only form of thermal cutting. The Oxy-Fuel cutting process uses a two-part torch, a preheating exterior oxy-fuel flame, and a jet of oxygen with a purity of 99.5% or better at the center. The cutting relies on a chemical reaction between oxygen and iron or carbon steel in the presence of heat. The exterior flame, produced by a mixture of oxygen and a combustible gas such as acetylene, propane, methane, or other gas, preheats the oxidizable metal to its kindling temperature, which is around 900 degrees centigrade. This is the temperature at which the metal reacts quickly with oxygen. Once the starting area reaches the kindling temperature, the operator turns on the jet of compressed cutting oxygen. The oxygen streams from the torch tip into the glowing red preheated metal, causing a fast combustion reaction between the steel and the oxygen. The resulting molten material, or slag, is blown through the metal by the stream of cutting oxygen. This exposes fresh metal to the cutting stream.
So now that you've learned a little bit about some of the separating processes like laser cutting and Oxy-Fuel cutting, let's look at one that might seem a little strange. Let's look at water jet cutting.
The abrasive water jet erosion process uses abrasive particles suspended in a high-pressure stream of water to cut a wide range of materials. Abrasive water jet cutting generates no heat and leaves no heat-affected zone, making it an alternative to thermal cutting. In addition, there are no toxic fumes, toxic wastes, or chemicals to cause problems. Dust is also non-existent. Abrasive water jet systems cut materials that gum up saws or suffer unsatisfactory heat damage in thermal processes. They are good at cutting laminates of different materials, including composite mixtures of metals and nonmetals. Thick materials may also be cut using the abrasive water jet process. The water pressure for water jet cutting is between 30,000 to 60,000 psi, or pounds per square inch. By comparison, ordinary household water normally runs at 40 to 50 psi.
Let's move on to the joining process. Joining processes may include everything up through a newer process of joining, such as rapid prototyping, which might be in the form of stereolithography, laminated object manufacturing, selective laser sintering, 3D printing, and fused deposition modeling, which is trademarked by Stratasys Incorporated. Or you might refer to that as fused filament fabrication. Stereolithography is a rapid prototyping process that fabricates a part layer-wise by hardening a photopolymer with a guided laser beam. The joining process is also referred to as the additive process. Other examples of this can include welding, gluing, soldering, and prototyping. Let's consider forming. Although some properties of the material may change, most do not. For example, a metal handle on a shovel may be bent to make the handle more ergonomic. Bends may also be added to strengthen a shape. Let's watch a video on forging.
Forging is the controlled deformation of metal into specific shapes by the use of compressive forces. These forces are applied through tools and dies, driven mainly by hammers, which deform the workpiece by high-velocity impact, or presses, which deform the workpiece through controlled high pressures. Forging is one of the oldest metalworking processes, dating as far back as 8000 BC. It is utilized today to reduce the cross-section, improve the metallurgical microstructure, provide directional grain flow, and eliminate porosity of cast ingot in fabricating wrought mill forms, and to form discrete parts to near net shape from these wrought mill forms, further refining microstructure and directional grain flow.
And also this video on metal extrusion.
Extrusion is the deformation of either metals or plastics forced under pressure through one or more die openings. The resulting shape is called an extrusion and is produced typically having a constant cross-section profile defined by the shape or geometry of the die opening. With special tooling, stepped or tapered extrusions may also be produced. Almost any thin or thick, hollow, or solid cross-sectional shape may be produced by extrusion. These extrusions are then typically cut to length for use as products, assembly components, or as raw stock for further processing into discrete parts. Extrusions are used for a variety of applications within many industries, including automotive, aerospace, building and construction, furniture, utility conduit, electronics, and many consumer products.
And if we're going to consider metal extrusion, let's consider plastic extrusion as well.
Plastics extrusion is a continuous process in which thermoplastic feedstock material in an extruder is transformed into a molten, viscous fluid using heat and mechanical shearing. This thermoplastic fluid is then forced through a die opening where it is shaped and cooled into solid form. These forms include bar and rod, tube and pipe, or profiles such as angles and other cross-sections, flat products such as sheet and plate, flexible film for bags and packaging, monofilaments, and wiring insulation. Thermoplastic feedstock is fed to the feed barrel from the hopper. Hoppers are typically vacuum-fed automatically, but may be filled manually. As the feedstock enters the feed barrel, it is driven forward by the rotation of the screw. The feedstock plasticizes or melts as the rotating screw drags it forward. This is referred to as drag flow. Drag flow causes the thermoplastic molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the feed barrel, bringing the material to its final temperature. Two of the principal plastic extrusion processes are profile extrusion and blown film extrusion. Profile extrusion is a horizontal process used to make long, continuous shapes having a constant cross-section or profile. The profile is extruded into a long horizontal cooling tank or trough filled with water. This water cools and solidifies the extruded plastic as it exits the die. At the end of the cooling tank, haul-off rolls pull the profile away from the die at a uniform, controlled speed. As the profile is pulled through the haul-off rolls, a cutter shears it to the required length for further processing. Some profiles are difficult to extrude because of shrinkage and the flow characteristics of the plastic. Typically, generous internal and/or external corner radii are used to minimize these concerns. Additionally, some profile extrusions may also require inline sizing to achieve dimensional tolerances. The blown film extrusion process uses an extruder to pump molten plastic vertically up through a die having a 360-degree annular opening on its top. This produces a tubular film extrusion, which is subsequently filled with air. As a result, the tube expands out into a bubble, having a diameter larger than the diameter of the annular opening of the die. The tubular bubble cools as it is pulled up. When sufficiently cooled, the bubble is flattened within a collapsing frame. The flattened plastic is then pulled through a series of rolls, commonly referred to as nip rolls. Nip rolls help to maintain tension on the flattened plastic film as it is guided to a winder and wound onto a core for later use.
Let's look at how forming can also be thought of as somewhat subtractive with this stamping dies video.
Stamping dies are the tools that shape and cut sheet metal parts. The design and production of dies is a specialized profession in which prepared drawings are translated into stamping dies by skilled craftsmen known as die makers. These stamping dies are then mounted in presses, where sheet metal is fed to them either individually as cut blanks or continuously from coils. There, the press provides the force to close the dies where they form the sheet metal into finished parts. The term die can be confusing since it represents two different things. As a generic term, it represents the entire press tooling used to cut and form metal. However, the term die can also refer to only the female half of the tool set. The male punch mates with the female die, and working in opposition to each other, they form shapes and punch holes in sheet metal. The term die set refers to the upper and lower die assemblies, which are also called punch and die holders or shoes, as well as other components. Die sets can take many forms, shapes, and sizes. The upper half of the die set is clamped to the press ram, while the lower half is secured to the bolster plate on the press bed. The die halves are opened and closed by movement of the press ram. Guide pins sliding in matched bushings or ball bearing bushings align the upper and lower half of the die set. Basic die operations include cutting, bending, forming, drawing, and squeezing. The two most common types of dies, however, are cutting dies and forming dies. Cutting, which includes shearing, blanking, hole punching, and trimming, is the most common press-working operation using dies. Shearing is a process by which large sheets of material are cut into smaller sections. These pieces are generally used in later operations. Blanking is a form of shearing that cuts sheet metal stock around the complete perimeter of a shape to form a workpiece blank. Reference to a blank in stamping usually implies the need to perform subsequent operations to the workpiece. Punching is the cutting of a slug from the sheet metal stock to produce a hole. After a part has been formed, a trimming die is utilized to remove the excess scrap metal from the workpiece. Forming is a broad term for metalworking processes in which the shape of a punch and die is reproduced directly in the metal. Some common forming operations done with press-mounted dies include drawing, bending, flanging, and hemming. Drawing shapes a flat pre-cut metal blank by forcing it into a die cavity with a punch without excessive wrinkling, thinning, or fracturing of the metal. Various complex forms may be produced by drawing. Drawn parts may vary in size from small parts up to aircraft and automotive parts large enough to require mechanical handling equipment. Bending is performed on sheet metal to gain rigidity and to produce a part of desired shape. Bending is usually done to make structural stampings, such as brackets, braces, and supports. Flanging is a forming operation similar to bending, except that the flanged edge is shorter and narrower compared to the overall part size. A flange can be bent down along a straight or curved line and is used for appearance, rigidity, edge strengthening, removing a sheared edge, and to provide an accurately positioned fastening surface. In sheet metal forming, hemming is utilized primarily to provide a smooth, rounded finished edge, and to attach sheet metal parts together. Multiple operations may be carried out on sheet metal stock either at a single die station or at multiple stations within a single stroke of the press. Dies used in single station operations can be either compound dies or combination dies. Compound dies are press tools in which only cutting operations are done, usually blanking and hole punching. Combination dies are press tools in which a cutting operation, usually blanking, is combined with shaping or forming operations. Multiple station operations are done with dies that have several stations. Each station simultaneously performs a single step in a series of operations needed to complete a part. Finished workpieces are discharged with each stroke. Multiple station operations can be performed using either progressive dies or transfer dies. In progressive die operations, parts are made from continuous coil stock and remain connected to the stock by a carrier strip during each successive operation until the final cutoff and discharge from the die. In transfer die operations, parts are blanked before or at the beginning of the sequential operations. Mechanical transfer devices grip and move the individual workpieces from die station to die station within a single die to complete a progression of operations. With large workpieces, a tandem press line may be utilized. Parts are transferred by gripping devices from press to press, instead of within a single die. Each press within the tandem line holds its own tooling and performs specific operations to form, trim, and pierce the part.
One last type of forming process is the hydroforming process. Let's take a look at how this is done.
In a typical hydroforming operating cycle, a blank is placed on the lower tooling. Then the press is closed. Fluid pressure is then applied into the tubular section or onto one side of the sheet metal blank. The magnitude of pressure is high enough to cause the blank material to deform plastically, taking the shape of the tooling. Lubricants are especially important in hydroforming. Lubricants assist in reducing the friction stresses or forces at the tool blank interface, thus improving metal flow. There are several advantages to hydroformed components over conventionally manufactured parts. Conventionally produced multi-component parts can be hydroformed from a single blank, reducing part count and possibly weight. Most, if not all, forming and piercing operations can be performed within a single hydroforming setup. And scrap rates for hydroforming can be significantly lower than traditional stamping scrap rates. For these reasons, many major industries use hydroformed components, including the automotive, aerospace, appliance, and plumbing industries.
No matter what type of process you may go through, any manufacturing process may involve steps that are referred to as finishing. This includes processes such as deburring, cleaning, coating, electroplating, painting, and assembly processes. Let's break down deburring. This slide will provide you with some images of some common burr locations found after machining and some hand deburring tools. Notice that there's an image in the bottom left-hand corner that shows various different sizes and types of tools that are used for deburring, as well as in the middle and on the right. These are pretty common. We have some of these in the Fab Lab as well. These are just the ends of the tools that stick into a handle that can then be rubbed around the edge of a material, removing the burr or leftover piece that's on the edge of the material that can be sharp or dangerous. These methods for deburring might include filing or scraping or even trimming. Another finishing process to consider is cleaning, which is typically performed in preparation for further processing. The unwanted material may be a soil or grime, some grease, or a scale or stains, blemishes, or even a corrosive deposit. Alkaline cleaning employs alkaline solutions. Parts are soaked or sprayed to promote the cleaning. Electrolytic cleaning have parts that are soaked in an alkaline solution and a current is passed through it, effectively cleaning the surface. Solvent cleaning have parts that are soaked or sprayed with a solvent that removes oils and greases. Vapor degreasing is a solvent cleaning with the vapors from a boiling solvent solution. Acid cleaning is an acid solution that's employed to dislodge solid dirt deposits from metal surfaces. Abrasive blasting has abrasive particles that are propelled by compressed air or water at a workpiece to dislodge undesirable matter. And abrasive wheels are, wheels that are made up of abrasive covered cloth that's spun over a surface to clean it. Coating is also a finishing process. Material will then protect the workpiece from atmospheric elements, which could cause corrosion or some other form of surface deterioration. Mechanical coatings, organic coatings, applied by brushing, spraying, dipping, and flowing include paints, varnishes and enamels, lacquers. Electrolytic coatings, also organic, applied by use of electrical energy could be things such as powder coating or electroplating. Conversion coatings, inorganic coatings, applied by chemical reaction include phosphate coating, chromate coating, oxide coating, and anodizing. Another type of finishing is assembling. This PVC pipe dog agility jump uses mechanical fastening. Mechanical fastening might be temporary, as in the case of the dog jump, so that it can be changed. In this example, the size of the dog using the jump will determine how high to set the jump. Mechanical fastening can also be permanent. If, for example, you have a large dog and you want the jump to stay at a certain height, it can be held together with screws. When using bonding, the bonding agent, glue or some other substance, must be considered. The two major bonding methods include cohesive, this is heat welding and or pressure welding, and adhesion, including solvent bonding, brazing and soldering, and adhesives. In addition, the method used to create the bond and the type of joint that will be used must be taken into consideration. And the final finishing that we're going to talk about is conditioning. Heat, mechanical force, or chemical action is used to change the internal properties of a material. An example of thermal conditioning is air drying lumber to make it suitable for construction applications. Lumber, intended for interior uses, is kiln dried, another thermal conditioning process. Ceramics are created using a thermal process called firing. The tires pictured were conditioned using a thermal process called vulcanization. Cement is an example of chemical conditioning. Water is added to the powder so that the chemical process may begin. Tanning of animal hides is also a chemical conditioning process. Mechanical conditioning occurs when physical force is used to modify the internal structure. This is achieved through pounding, squeezing, or even spraying shot against a part.